In this video, we're going to start our conversation about this idea of motion and how we describe motion. And in this video, we're going to really be focusing on how would you describe motion in terms of a graph, and specifically here in terms of a displacement versus time graph. So to get into this, it's important for us to discuss this idea of motion. Now, motion is a word that you are all familiar with. We know if something is moving or if you yourself are moving. But if you really think about it, motion has a layer of complexity behind it as well. So if you're looking or watching this video on a laptop or an iPad screen, uh, you would probably say that your iPad or your laptop is not moving. And that is true, but it is true only relative to you. If we are measuring its motion relative to the sun, it is moving really, really fast because the Earth is rotating, but it's also revolving around the sun. If we're measuring it to the center of our galaxy, the sun in the solar system is moving about the center of our galaxy, and the galaxy itself is also moving through space. So we would say that motion has to really be defined as an object's change in position relative to a certain reference point. So another example, this astronaut moving relative to Earth is about 17,500 miles per hour, but relative to the space shuttle, not moving at all. In this class, we're not really going to get into any tricky scenarios, and if it is, you will notice that there's something funny about that problem. So here, you can probably just assume that we are always going to be measuring relative to the observer, which ultimately means relative to the environment itself. So if we're going to get into ultimately to graph the motion using a displacement versus time graph, it's important that we understand what displacement actually means in this case. And it's very similar to another word that you're probably familiar with, distance. Distance is how we describe how far we have traveled. If you're driving in your car, your distance is what the odometer is saying. It's how many miles the car has gone total. It doesn't matter where you're going, it's just how many times the wheels move around. If you're running or walking, it's how many steps you've taken. Doesn't care about where you've gone. It's just how many miles or meters or kilometers you have traveled in total. Displacement, on the other hand, is relative to where you start. So displacement is how far are you from where you began? How far are you from the origin? Now, it's probably easiest to actually see this in terms of a picture. If we're going to display this in a two-dimensional picture, say we go to Google Maps and we try to figure out how would we travel from the Minnetonka High School to Niagara Falls. Say we want to take a class trip to go see the waterfall. Um, to do so, you would have to travel this blue line here because we are restricted to roads if we're going to drive there, which means we have to go all the way around the Great Lakes to ultimately make it to Niagara Falls. And by land, that would take us a pretty decent journey. But as the crow flies, we could go straight there. That's how far we are from the origin. Doesn't care about the total uh, path that we took to get there. Just straight line to get to where we need to go. We would call that as the crow flies. So in this picture, blue would be our distance that we traveled, and red would be our displacement. It's even easier, I think, to see this in one dimension. Say we have an example where you're walking a pretty good distance here. You walk 5 kilometers east, then you turn around and you walk 2 kilometers back west. Notice that this arrow is starting from where we left off because we didn't start back at the beginning. Then you turn around and you go another 4 kilometers east. If I wanted to know the distance that I traveled here, I would just add up the total steps that I went. Doesn't matter going backwards or forwards. I would take that 5 plus that 2 plus that 4 added together, and I'll get 11 kilometers. That is my distance. That's how far I have totally traveled. Looking at this picture then, and that idea of displacement being how far you are from where you started, what is the overall displacement of this journey? The nice thing about this diagram is you can actually see, because it's marked out relative, if you're starting at 0 and ending at 7, your overall displacement is going to be 7. It's how far you ended from where you began. And that's 7 kilometers away. Now, you could have traveled hundreds or thousands of kilometers in between beginning and ending, and your displacement still would have been 7 as long as you ended up at this point right here. Now, we can actually graph this as well. If we make a graph with position on the y-axis and then time on the x-axis, we're just going to graph this in two axes rather than just one going back and forth. Now, in this class, like some classes that you'll see, will describe this as position. In this class, in IB, we're actually going to call this displacement. It's going to mean essentially the same thing, just where you are relative to that 0 point, where you started. Now, the only difference in this graph is now we have time going over our journey as well. And just for simplicity here, we're not going to give any units to time. We're not going to care about what the time is. We're just going to say over some duration of time, we have traveled from 0 to 5. And then we turn back around, and then over some duration of time, we go back down to 3. And some duration of time, we go back up to 7. So here we can still figure out our total distance. We went 5, and then we back 2, and then we went another 4. Our total distance is still 11, and our total displacement, we ended at 7, we started at 0, our total displacement is still 7. So before we get into describing in a lot of different types of graphs, these types of motion, I think it's useful to use another analogy. There's a photography trick called stroboscopic photography that allows us in one still frame image to see an object's motion over time. And to do this, it's helpful to to imagine yourself in a really dark room where you can't see anything, and there's a strobe light that's flashing in this case, every 0.04 seconds. So pretty fast. And since it is totally dark in this room, you can only see where objects are whenever the strobe light turns on. So if the strobe light's off, you have no idea where an object is until the light turns back on. And that means that if an object is moving really fast, it is going to travel a long distance during that time. A fast moving object looks something like the soccer ball here towards the bottom of its fall. A slower moving object is going to look something like the top here, where the object is really close together because since it's moving so slowly, it doesn't travel very far in between that same time duration. Now, this works again because the duration between these captures, the time that happens in between, is exactly the same every single time because it's a very consistent strobe light. We can also use this to talk about if the object is moving at a constant velocity or if it's speeding up or slowing down, if it's accelerating. A constant velocity in a picture like this just means that the increments in between captures is always going to be pretty consistent. This billiard ball moving across the screen is moving at a relatively constant velocity because the spacing here is almost always the same. On the right-hand side, though, we can see that spacing changes. It gets faster as the object goes down because the spacing is getting larger and larger. We would say that that object is accelerating. So as a general rule, here in a stroboscopic photograph or one of these dot graphs, we would say that the more spacing there is between pictures, the faster the object is moving. Now, we can see this in a variety of different examples, and one of my favorite is this video of a cat. So in that video, at some interval of time, you can see where the cat is, but only when you're observing it. So just like one of those stroboscopic photographs or the position dot graphs that we'll see in a little bit, you can see it only in certain durations of time. Now, before we get into graphing, I want to give you a challenge here just with numbers themselves. So if, let's say I have three carts, cart A, cart B, and cart C, and I tell you at 0 seconds, these are where the carts are at, you should be able to predict from this which of these carts might get to the 10-meter mark first. Now, your prediction isn't based on much, it's just based on its starting position. But if I give you a little bit more information, and I say, all right, at 1 second, they're all at 4 meters. Um, Now you have no more information than you did before. I would like you to predict which of these carts is going to make it to the 10-meter mark first. Okay, so obviously it's not just an even tie. It is at this particular moment in time, but they all had a different position the second before. So it's useful now to see how does this motion continue? What's going on here? So I'm going to give you one more second ahead. And we can see that some patterns start to emerge here. So for example, cart A was at 0, and then it's now 4 meters ahead, and then it's now 3 meters ahead of that. So you can expect that it might be maybe 2 meters ahead of that. It might continue this pattern. It looks like it's traveling less and less distance every time. Same thing with cart B. We see that it's going 2 meters, then 4, then 6. It looks pretty consistent, so I might expect that that would turn into an 8. I would like you to predict where do you think cart C will be at the end of that 3 seconds? All right, so if I give you your answers here, you can see that these carts are all pretty close to the same position at 3 seconds. But if you remember back, our ultimate question was which one is going to get to 10 meters first? Now, we could start to make predictions here, but it's going to be more useful if we graph this. If we put this in a graph and then place a dot for each of these carts with their known positions. So if this is our position or displacement and this is our time, we can see that these pictures start to tell us a little bit of a story. If we look at cart A, that story, like we mentioned before, it's moving less and less every second that it's traveling. It went 4, then 3, then 2, then you can expect probably the next one's going to be 1. We would say that that graph looks like it's sloping or changing its slope. It's curving downward. Green, in this case, is moving pretty straight and steady. And purple, uh, every second provided more and more displacement between its position and the second before. So we see that sloping up, curving up. These pictures here are going to be really important to us in a minute when we're talking about describing actually what's happening to an object's motion, because it's more than just position. You need multiple frames of an object's position to know what its motion is going to be. From one or two snapshots, you don't know if it's constant or speeding up or slowing down. You need multiple frames in time to see that. So let's look at an object that isn't moving at all. Like, what would that look like? If I place an object here at the 4 mark, and then over time watch to see where it went, and say it didn't go anywhere. Over time, every second, I would just mark where it is always at 4. So it's a pretty boring graph, right? It's always going to be at the same displacement. So we just draw a line saying it's at 4 the whole time. It's always going to be there. Now, let's make it a little bit more interesting. Let's say that this object is moving forward. I'm going to animate this object and then place a dot every second to show you its position every second. And then on this displacement versus time graph, every second, place a dot corresponding to where it was there. And you see that this graph is moving upward in a very linear way. We can graph that and show at every even increment of time, it's moving in even increment of displacement. That's similar to that cart B in the example that we were looking at. We can also describe an object even if it wasn't moving forward. We say that this is moving forward because it's going away from 0 and towards higher numbers. And in this case, I've oriented this in a vertical sense, but you could orient it horizontally as well and say that an object's moving forward, like if you were in your car moving forward or moving backward. Now, if I want to say an object's moving backward in this vertical plane, we would say that the object is falling downward from 7 back down to 0. But in this case, it's still going to be consistent or constant motion because there's an even spacing. It moves one every second, and we can plot that in. If we wanted to see more than one velocity, though, now let's get a red and a green object here, and we'll play them both. And we can see very clearly that the green is moving faster than the red. So let's talk about how we would describe that in this graph. We can make the red graph exactly the same way that we were making it before. We can allow it to move and then figure out its position at every second along the way, and then go ahead and graph that. We can do the same thing with green. And notice now at every second, it's actually moving farther than the red one. Just like a stroboscopic photograph, you have more travel between the same interval of time. So that's spread out. It looks like it moves 2 meters for every second that we go. So we can plot that, and it looks something like this. Um, in our next day's lesson, we're actually going to talk about calculating a velocity from this, but you can see right here that the slope is showing us if an object is moving slower, like the red one, or faster, like the green one. And faster still, we'd expect it to even be steeper, steeper still. Now let's look like what would happen if an object wasn't moving constant the whole time. So in those last examples, at every interval of time, every second, if we were to draw a dot where the object was, it was always an even spacing, whether it was one or two, like the green one. But if we have some object that's speeding up, so we graph this and we see that every second is moving faster and faster, which means every second there's a farther and farther spacing between the dots. But notice here on the displacement time graph, horizontally, each dot happens at an even spacing because we're using the same principle of the strobe light here that every second we add a new dot. So no matter where it is, we're going to place that dot at that second's mark. And notice here, we see that the spacing gets bigger, but when we spread that out over time, we see it makes this nice curving trajectory. Now, thinking back to the last example, the steeper the slope, the faster it was moving. That still corresponds here. We know that it was moving fastest at the end here when the spacing was the farthest. So that gives us the steepest slope, and it wasn't moving as fast here when the objects were close together, which gives us the shallowest slope. So this is what we would call speeding up, but it's still moving in the positive direction. We can also speed up if we're moving in the negative direction. So here's an idea of what that might look like. It's still getting faster and faster as it goes because the spacing is getting farther and farther apart in those intervals of time. Now what our graph looks like is we still have a curve, but in this case, the curve is sloping down and getting steeper and steeper in the negative direction. So it's moving closer to zero. It's moving in the negative direction, but we still say that it's speeding up because it's the slope of this graph that tells us how fast it's moving. So if I were to put those two graphs together on the same screen, I said that these are both graphs that are speeding up. What about these graphs is similar to tell you that these are graphs, displacement versus time, indicating something getting faster? Okay, hopefully you're able to see at this point that the biggest thing here is as time moves on, the graph is getting steeper. It doesn't matter if it's steeper in the positive direction or steeper in the negative direction. That steeper slope means that it's traveling farther for every second that it's moving. Now let's look at some even more examples here. We saw some examples of speeding up. Now let's look what would happen if we were to make that object slow down. So in this case, it starts out fast, and we can see evidence of that because it's spread out a little bit farther, but then it slows down. The spacing gets closer and closer. Graphing at even intervals of time, we see that that graph curves and levels itself off a little bit. So we would say that that's slowing down. Also, we're saying that it's still moving in the positive direction. It's still going away from zero in this case, but slowing down the whole time. We can also represent an object slowing down but moving in the negative direction, which means, again, we're going to start moving fast in the negative and then slow down as we get closer and closer to zero. And again, you see this picture start to form. And notice that all of these pictures, when the object is changing speed, are all coming out curved in some fashion. This curve in a displacement versus time graph indicates a change in velocity. It's not an even slope every single time. So here are those three changing velocity graphs. So looking at these, we've got A, B, C, and D. I've got two questions for you. The first question is, which of these, and there will probably be more than one correct answer, you should indicate all of them, which of these graphs indicate an object that's moving in the negative direction? Moving in a negative direction, again, means that your number in this case is getting smaller. Since we're all positive here, getting closer to zero. So this graph B is representing an object moving in the negative direction because it's going from 6 down to 0. Object graph C is also moving in the negative direction. It's getting closer and closer to 0. Now my next question for you is which graphs represent an object that is slowing down? Again, you can select more than one graph, and you should if there's more than one graph that corresponds. And you can still choose some graphs that have been chosen in the past question as well. All graphs are eligible. So if we look at this question, a graph that's slowing down means that the slope is leveling off. It's kind of getting a shallower and shallower as it goes. So graph A is definitely slowing down, moving in the positive direction. But graph C is also slowing down because it started out with a steep slope and then it got shallower and shallower as it went. So with that in mind, the main takeaways for this lesson, after this, you should be pretty comfortable describing the difference between distance and displacement, how far you travel versus how far you are from where you started, the origin. You should be able to calculate distance and displacement for one-dimensional motion, like that example where you're walking back and forth. You should be able to plot constant velocity on a displacement versus time graph, a nice straight line, relative to how fast it's going. Steeper is faster, shallower is slower. And you should be able to plot a graph that is changing its velocity, one of those curved graphs where it's either leveling off or it is getting faster, it's getting steeper and steeper. And then finally, given some examples, you should be able to tell me if a displacement versus time graph is moving positive or negative, or if it's speeding up or slowing down.